Hey everyone! In this video we will introduce some expected value results for working with linear functions. So we'll focus on linear functions of random variables in this section because these linear functions and random variables occur very often in statistical practice. So we often encounter linear functions of sample values. So say we have a sample y1, y2, yn. A linear function that we might be interested in calculating is something like the sample mean. We'd like to know eventually how that sample mean might be distributed. So let's start working towards some results related to that. So let's start by looking at a function, just a simple linear function with constants. So let's say that a1, a2, all the way through an are constants. We might want to find the expected value and variance of some variable, say u1. That's a linear function of a1 times y1 plus a2 times y2, and so on. We might also be interested in something like the covariance between two linear combinations, u1 and u2. So let's take a look at some results here. We'll define two linear functions of random variables, u1 and u2. So u1 will be defined as the sum of ai times yi. u2 will be defined as the sum of b sub j times x sub j. Then the following results hold. So for the expected value of any of these linear functions, we can find it by taking just the sum of the multiplier, so the a's, times the mean of that random variable, times the expected values of the y's, or the x's. We will find the variance like this. So we'll find the variance by taking the sum of the constant a squared times the individual variances of the yi's, plus the double sum, where over all pairs where I is less than j, of the constant ai times the constant bj times the covariance of y and x. So these two random variables. Again, here I'm using y and x just to kind of make it a little bit clearer that these are two different or distinct random variables. The double sum is over all pairs where I is less than j. So we'll add up the constants times the covariances times 2. To get the covariance then between the u's, so between these linear functions themselves, we'll take the sum of the constants times the covariances. So let's put these formulas into practice to see how they're actually going to work. We'll let y1, y2, y3 be three different random variables. The expected value of y1 is 1, the expected value of y2 is 2, and bucking tradition, the expected value of y3 is -1. y1 and y2 have the following variance-covariance matrix, and here's how you would read this. The diagonal elements in a variance-covariance matrix represent the variance of the random variables. So for example, the variance of y1 is 1, the variance of y2 is 3, and the variance of y3 is 5. The off-diagonal elements represent the covariances. So the covariance between y1 and y2 is -0.4. The covariance between y1 and y3 is 0.5, and the covariance between y2 and y3 is 2. So let's find the expected value and variance of this linear function u. u is equal to y1 minus 2y2 plus y3. So let's start with just the expected value here. We can find the expected value by distributing across and pulling out constants. So our expected value of u is the expected value of y1 minus 2 times the expected value of y squared, or y2, plus the expected value of y3. So we get -4 for the expected value of u. The variance of u is a little bit trickier. So to find the variance of u, we'll take the sum of the constant a squared times the individual variances, so we've got 3 terms in the summation, plus 2a1, a2 times the covariance of y1, y2, plus 2a2 times the covariance of y1, y3, plus 2a2a3 covariance of y2, y3. So plugging all of those values together from the variance covariance matrix, we get a variance of 15.3 for the linear combination U. Now we'd like to find the covariance between two linear combinations. We have U and we have W. W being 3 times y1 plus y2. We'll find this by taking the sum over all pairs of yi and u and yj and w. So we have 6 terms that will go into this. We'll start by taking a1, so the constant on y1 and u times the constant on y1 and w times the covariance of y1 and y1, or just the variance. The constant on y2 and u times the constant on y1 and y times covariance of y2, y1, and so on. So we'll have those 6 terms that we'll add together. We get a covariance between these variables of 9.2. So let's let y1 and y2 be independent random variables with expected value of yi being mu, variance being sigma squared. I'm going to define the sample mean, y bar, as 1 over n times the sum of the y's. Let's show that the expected value of the sample mean is the expected value of the individual y's is mu. Let's also show that the variance is sigma squared over n. One thing I want to point out, and I'll remind you of this again a little bit later on, we have not made any assumptions about how these y's are distributed. So let's make a further assumption here. We're going to assume that these y's are independent. If we can't make that assumption, then when we go to calculate the variance, we'll need to add in all of those covariances. So we'll simplify our lives and assume that these are independent y's. Assuming independence here, we can get the expected value of the mean by taking 1 over n times the sum of the expected values of the y's. So we get 1 over n times n mu, or mu. The variance becomes 1 over n squared times the sum of the variances. So we have then plus 2 times 1 over n squared times the covariances. Assuming independence makes this term drop out because those covariances are 0. So that's why we like this assumption. So we get 1 over n squared times n sigma squares, so sigma squared over n for the variance of the sample mean. Let's take a look at another example. So suppose that the number of defectives y in a sample of n items selected from a manufacturing process follows a binomial probability distribution. One estimator that we can use for the fraction of defectives in the lots, let's say we don't actually know what this p is going to be, is the random variable, p hat, y over n. Let's find the expected value and variance of this random variable. In order to do this, we'll make use of the relationship between a binomial and a Bernoulli distribution. The binomial distribution is really just the sum of n different Bernoullis. Think of a Bernoulli like an individual coin flip. It takes on values of 0 and 1. So when we approach it this way, our sample proportion p hat is actually just a sample mean. So let y be considered the sum of the x's. Each of these x's is distributed Bernoulli with parameter p. So the expected value of p hat becomes 1 over n times the sum of n Bernoullis. So 1 over n times the expected value of a Bernoulli. The expected value of a Bernoulli random trial is p. So we get the expected value of the sample proportion p hat to be p. The sample proportion, again, is just a mean, so we can use the result that we have shown for the mean variance as well, again, assuming independence here. The variance of a Bernoulli random trial is p times 1 minus p, so we get 1 over n squared times n times p times 1 minus p, or p times 1 minus p over n. So in the next video, we will continue by looking at conditional expectations, and that will be our last topic for bivariate distributions. I'll see you then.